I'm Faraz Ahmad, and the topic of my talk today is ShuffleWatcher, shuffle-aware scheduling in multi-tenant MapReduce clusters. This work was done in collaboration with Srimat Chakradhar from NEC Labs, Anand, Raghunathan, and Vijaykumar from Purdue University. So let's get started. Recently, large-scale clusters are becoming more and more multi-tenant because they reduce cost, improve utilization, as well as enable data sharing among users and jobs. In a typical multi-tenant environment, there are many users submitting MapReduce jobs to the cluster. At any given instant of time, there are multiple jobs going on, running in parallel onto the cluster. The cluster administrator is faced with the challenges to improve throughput, latency, as well as fairness among users. So as part of our contribution in this work, we achieve high throughput and low latency while we want to maintain the underlying fairness policy. While we are all aware of the MapReduce scheduling mechanism, I would particularly like to highlight the significance of shuffle in multi-tenant clusters. So this shuffle is an all-map to all-reduce communication, which transfers data from all map tasks to all reduced tasks, and it translates to all-node communication, stressing the bisection bandwidth. Now, MapReduce jobs can be categorized into two types of jobs based on the amount of data they shuffle. We can categorize them as shuffle light and shuffle heavy jobs. And recent studies on Facebook and Yahoo cluster indicate that there is a significant fraction of jobs which are shuffle heavy. And another important point to make is that these shuffle-heavy jobs run much longer than shuffle-light jobs. So they play a very significant role determining the overall throughput of the cluster. In a typical multi-tenant environment, there are multiple jobs running at the same time, so they shuffle together and stress the network bisection bandwidth. As a net impact, we come into having a low cluster throughput and high job latency because network becomes the most critical resource. So let's go through briefly the related work in multi-tenant scheduling. There have been a lot of work that targets fairness in multi-tenant clusters. FIFO scheduler, capacity scheduler, fair scheduler are part of the Hadoop release as well. There was another paper, NSDI 11. This was called as dominant resource fairness, where they want to maintain fairness among users based on the dominant resource. In terms of targeting throughput, there are two most significant works. One is delay scheduler in Genesis 10, and another is Quincy in SB09. And these papers target improving the cluster throughput by optimizing remote map traffic. By remote map traffic, I mean executing a map task on a node which does not have data locally available. So in the table below, I show that what's the contribution of different types of traffic in a multi-tenant cluster. And here we can see that shuffle plays a very significant role, and it has a huge fraction of data doing the travel along the network. So our contribution in this work, so basically this shuffle motivated us to do some more research on it, and our contribution over here is that we improve throughput by focusing on shuffle while maintaining fairness among users. So these are a list of contributions for ShuffleWatcher. ShuffleWatcher achieves high throughput, low job latency by shaping and reducing shuffle traffic. It leverages factors that are unique to multi-tenancy and exploits a trade-off between intra-job concurrency and shuffle locality. I'll briefly explain what those are in coming slides. So ShuffleWatcher employs three key mechanisms: network-aware shuffle scheduling for traffic shaping, whereas shuffle-aware map placement, shuffle-aware reduce placement for traffic reduction. And again, the key important point is that we keep the underlying fairness policy intact. In all, ShuffleWatcher achieves 46% high throughput, 32% lower job latency, and 48% reduced network traffic compared to delay scheduler. So this is a brief outline of my paper. I have already gone through the intro. Now I'll quickly go through the ShuffleWatcher mechanisms. Then I'll do present some experimental methodology, followed by some results, and finally conclude. So let's now first go to our first mechanism, network-aware shuffle scheduling. For network-aware shuffle scheduling, we make two key observations. The one is that while, as I mentioned, the network bisection is a huge bottleneck in a multi-tenant environment, we make the key observation that network is not saturated all the time. So as we can see in the graph, there are periods where network is saturated, but there are also periods where the network is not saturated at all. So we can use this observation to move traffic around so that we can more easily shape the traffic and improve the overall throughput of the cluster. Again, an important point I want to make over here is that simply delaying a job so that we can shape traffic is not an option over here, because it definitely compromises fairness. For the second observation, I'll first like to go through how things happen in a single tenant environment, where we schedule reduced tasks way ahead in the map phase so that our shuffle can overlap with the map phase computation. So by that, we can improve the intra-job map-to-shuffle concurrency, and we can overlap most of the communication with computation. So this is the insight behind why do we schedule reduced tasks way early in the map phase. In terms of multi-tenancy, things happen pretty much the same way in terms of execution. We should not compare the execution times of multi-tenancy with single tenancy, because in multi-tenancy, we expect that the job runtimes will be longer because they share only a part of the cluster to execute. Now, in terms of multi-tenancy, previous schedulers adopt the same policy, whereas we make the observation that if the network is saturated or there's a huge pressure on the network, we can dynamically schedule this reduced tasks so that on the very extreme, it can be scheduled at the end of the map phase. If we do that, we can more efficiently schedule our shuffle so that our execution time does not get hurt. And again, we can overlap the computation of this shuffle with the computation from other jobs tasks. So that overlap of communication and computation is also not lost. And while those resources which are freed by shuffle, we can execute tasks from other jobs to occupy. And this way, we can improve throughput of the cluster. So these are our two key observations. And based on that, what NAS does is it can delay a job shuffle at high network load. So it plays a key role in shaping the network traffic. So that's how it tries to shape the network traffic by dynamically scheduling reduced tasks, which dynamically schedule shuffle in the cluster. And at very high load, if we delay this shuffle, we can schedule tasks from the same job so that we do not affect fairness of the same user. For our second mechanism, shuffle-aware reduced placement, I would like to first go through how things work again in single tenancy, where there is one single job occupying the entire cluster, and then there basically to achieve high concurrency, the task occupies all the nodes. So in terms of intermediate data distribution, data is pretty much evenly distributed across all the clusters, so we can schedule reduced tasks anywhere. In terms of multi-tenancy, when there are multiple jobs running at the same time, all jobs do not get to run on all nodes or all racks of the cluster. And this is due to mainly attributed to dynamic scheduling, load balancing, fairness, as well as the map locality constraints which we have to follow. So in terms of intermediate data distribution, we get a skewed intermediate data distribution, whereas in this particular example, we can see that this yellow job just gets to have a huge share in terms of intermediate data on the first two racks. And for the blue colored job, it gets most of its share on the middle two racks. So based on that, our observation is that a job's intermediate data is likely to be secured in a multi-tenant environment. And the other observation that we made in NAS, that NAS can dynamically delay the scheduling of shuffle. It means that in some cases, we may be scheduling shuffle or reduced tasks at the end of the map phase or towards the end of the map phase. So by the time we schedule reduced tasks, we already know that how much intermediate data is residing on how many racks. So based on that, we can proportionally distribute our intermediate data onto the racks so that we can localize shuffle traffic onto those racks, and fewer traffic has to cross across the racks. So this way, we improve the shuffle locality. For our third scheme, shuffle-aware map placement, on the left side, again, we have the same map execution, which I presented a couple of slides ago. On the right side, what we see is that an ideal placement for map tasks so that we can have maximum shuffle locality. So if we can concentrate all the tasks of one job onto as few racks as possible, we can have maximum shuffle locality. So this is the key insight behind what we can do on map side. Now, if we just try to do that, we can hurt the remote map traffic a lot if we just randomly pick one rack and try to schedule a task, a job on that particular rack. So what we do over here is that we exploit the input data redundancy to provide this flexibility in map scheduling. So input data redundancy is that replicated input data, which is there replicated due to fault tolerance reasons. So we can pick and choose which replica to pick for to schedule a task over there. So by doing that, we can make a clever decision that, okay, where to place or where to concentrate this job on this particular cluster. Once we can do that, we can not only reduce the remote map traffic, but we can also improve shuffle locality. So our target over here is to reduce the sum of remote map traffic and cross-rack shuffle. So in some cases, it might happen that we may incur more remote map traffic compared to our baseline, but in all, we reduce the overall cross-rack traffic. So this is an overall picture for our ShuffleWatcher where we combine all the pieces together. ShuffleWatcher's main heart scheduler is NAS. NAS coordinates with a NetSat daemon, which is sitting there monitoring the network traffic. So it monitors shuffle traffic, it monitors how the data is moving for remote map, and also it monitors how the output data write is being moved across the cluster. So based on that, and it can also incorporate other jobs which are also running in parallel with MapReduce. So it can basically make a decision whether any links, whether any network is being saturated, and it provides that information to NAS. And based on that, NAS makes the key decision that, okay, what task to schedule now at this instant of time, given the network condition is this much. For example, if the network condition is that network is pretty heavily loaded, we can schedule a compute-intensive task which does not put any pressure onto the network. So shuffle-aware map placements recommendations become handy for the NAS scheduler. And in case the network is pretty low, network consumption is pretty low, then in that case, we can take recommendations from SARP and schedule those reduced tasks which have heavy shuffle traffic. And this way, we can not only shape traffic, but we can also help reduce traffic with the help of SAMP and SARP. So now I'll quickly go through the experimental evaluation and then finally present some results. So our baselines over here are fair scheduler, delay scheduler. These are already part of the Hadoop release. DRF scheduler is, again, dominant resource fairness scheduler, and it was re-implemented by our team in-house. The platform is 100-node Amazon EC2 cluster, where we have 10 racks of 10 nodes each, and 50 Mbps is the cross-rack per node bisection bandwidth. In terms of workloads, our job submission follows an exponential distribution, which is the same as was in the experienced in the real-world workloads of Facebook and Yahoo. The mean arrival rate was set so that we can achieve the highest throughput for our baselines. In terms of picking different jobs, we picked jobs from 12 real-world map reductions. They were a combination of shuffle-heavy, shuffle-medium, and shuffle-light jobs, and the job size also varied between 100 MB to 1 terabyte. So let's first do the throughput comparison against baseline. On x-axis, we present different schemes. The first three schemes are ShuffleWatcher, Fair, Delay, and ShuffleWatcher Relax. All of these schemes are normalized against Fair scheduler. So on y-axis, we have normalized throughput. So higher is better in this particular case. For delay scheduler is, which is the second bar, is based on the premise that we can improve map locality by relaxing the fairness notions a little bit. So we can skip a user's turn a couple of times just in a hope that, okay, we can get a node which has some local data available. So it's based on that premise. And for ShuffleWatcher Relax, we also implement the same thing. We also relax the fairness to the same extent to do an apples-to-apple comparison. So over here, we see that we improve throughput in all of the cases. The fourth bar is ShuffleWatcher DRF, which is normalized against DRF scheduler, and it's the same thing, like we improve throughput in that particular case as well. So our bottom line is that ShuffleWatcher is independent of fairness policy and improves throughput over multiple schemes. In terms of job latency comparison, we see that, again, the x-axis is the same thing. On y-axis, we have normalized execution time based on their particular baselines, and lower is better in this particular case. And we again see that ShuffleWatcher improves latency by 27%, 29% over the baseline fair scheduler, whereas 32% over delay scheduler, and 29% for DRF. So these are the job latency comparison. So here again, I want to make the key point that we not only improve throughput, which might be more intuitive to realize, we also improve the job's latencies, not only by reducing the overall traffic, but also by the help of different schemes which we employ through NES, SAMP, and SOP. The cross-stack traffic is our final comparison, where again on the x-axis we have the same baseline, and on y-axis we have normalized traffic volume, and again lower is better. And in this particular case, again, we see that ShuffleWatcher achieves significant traffic reduction, 36%, 48%, 35% over multiple schemes. So finally, to conclude, Shuffle plays a significant role in multi-tenancy performance, achieves high throughput by shaping and reducing traffic. The key points we make over here is that in terms of reduced task scheduling, we can be more clever in scheduling reduced tasks because the scheduling of reduced tasks is accompanied with shuffle traffic. And in terms of SARP, we make the key observation that we can be more clever in scheduling reduced tasks, where to schedule those reduced tasks rather than just randomly pick any rack or any node to schedule reduced tasks on. And again, in terms of SAMP, we made a key observation that rather than just picking any replica to schedule map task on, we can be more choosy and pick whatever replica is more suitable to make our shuffle more local. So these are our main contributions. In all, ShuffleWatcher achieves 46% high throughput, 32% lower job latency, and 48% reduced traffic compared to delay scheduler. Thanks.
So we have time for a few questions. Please introduce yourself and give your name and organization before you ask a question.
Hi, Peng Wu from Huawei. A question, can you talk about the related work in this area in terms of multi-tenancy?
Yeah, I talked about related work a little bit. I can highlight that work again over here. So not only we target so there are works which target fairness, but then there are also work which target throughput. And in terms of our more relevant works become delay scheduler and coincidence scheduler in this regard, where basically they do not optimize more on the shuffle side, but rather on the map execution side. So that's the most significant related work in this regard.
Right. I was just wondering, for example, for Google or Facebook, do you know what they are doing in this area?
I am not aware of anything which has been published yet, but yeah, so I don't know what's internally going on over there, but I'm not sure about any published work.
Thank you.
Thanks.
Okay, if there are no other questions. I have a question. So have you looked at what effect speculative execution would have on your overall running times?
You mean specular execution?
Yes.
What do you, how do you describe specular execution like?
So if a job is running slow, launching additional tasks, either on the map side or on the reduce side.
Yeah, we could do that, but again, that depends on how we define our fairness policy. If the fairness policy allows that particular job to occupy more resources, then yes, we can do that. But so it all depends on how we pick and choose our fairness policy. If fairness policy is based on, okay, whichever job requires more resources, give that job more resources, then yes, we can go ahead and do that. So it's all depends on how we proportionally distribute resources among different jobs of the different users. So this is how we go with that.
All right, let's thank our speaker again.